create induced EMFs, currents, and that keeps our economy going. Here is again one of those loops. Conducting wire, and I don't care about the direction of the magnetic field. If you want it this way, that's fine. What matters is that we're going to rotate it about this axis. And as we rotate it about this axis, we're going to get an induced EMF. And that induced EMF, which we derived, I think it was last lecture, as a function of time, will be a sinusoidal or a cosinusoidal curve, and therefore will look something like this. I call this loop number 1, and so this is the EMF produced by loop number 1. But now I'm going to add 2 more loops which are not electrically connected, physically separate. If you look from this direction, you will see the following. This would be your loop number 1, because you're looking in this direction and you would only see the conducting wire like so. I have now a second one which is rotated 120 degrees, and so in this picture you will see it like so. Loop number 2, and this is 120 degrees. Physically 120 degree rotated. And then I have a third one which is again 120 degrees rotated, which is like so. And so this angle here is also 120 degrees, and so this angle is 120 degrees. And this is my loop number 3. And so each one of those will give an EMF that has this shape, but they are offset now in phase by 120 degrees. And so they're all rotating in exactly the same way, like so. And so the second one will give me an EMF, if I try to estimate that roughly, something like this. So this is loop number 2. Comes a little later in time, and number 3 will again be offset. Will look like this. Number 3. And what we call this a 3-phase current. And a 3-phase current can produce a rotating magnetic field. We will make one for you, but I'll first explain to you how that works. So if the period of number 1 is 60 Hertz, then the period of number 2 is also 60 Hertz, and number 3 is also 60 Hertz, but they're just offset in terms of the phase angle. Suppose you're looking down onto a horizontal table. So this is a horizontal table. And I have here a solenoid. This is one and the same solenoid. When the current runs clockwise here, it will also run clockwise there. But it's open here. Going to put something in there. We call this number 1. Then I have another one which is rotated, physically rotated 120 degrees. It's here. Also coils. And I'm going to feed current number 2 through those coils later. Through those coils. This is number 2. And I have a third one, and I'm going to run current number 3 through those. So here are coils. Here are coils. This is number 3. And so 1 sees current number 1, 2 sees current number 2, and 3 sees current number 3. At the moment that the current through number 1 reaches a maximum, the currents in 2 and 3 are down by a factor of 2. You can check that for you. During my lecture, I went a little bit too fast over the part that is coming up now. So I'm going to redo it a little slower to make it more clear. When the current through loop 1 reaches a maximum, let's say then that the magnetic field due to loop 1 is in this direction. The current through this one and the current through this loop are 2 times smaller. You may want to check that. But it just so happens that the vectorial sum of the magnetic field produced by loop number 2 and by loop number 3 also happen to be in this direction. So the net magnetic field is in this direction. Let's now look 1/3 of a period later in time. Now the current in loop number 2 reaches a maximum. So its magnetic field is now in this direction. And you guessed it, of course, that it just so happens that the vectorial sum of the magnetic field produced by the other 2 loops is now also in this direction. And if we now look again 1/3 of a period later, when the current through loop number 3 reaches a maximum, then the magnetic field will be in this direction, and the vectorial sum of the magnetic field of the other 2 loops will also be in this direction. And look now what has happened. In one complete period, the magnetic field started out like this. 1/3 of a period later, it was like this. And 1/3 of a period later, it was like this. So what we have created is now a rotating magnetic field. And it rotates in one period, all the way around, 360 degrees. Okay, let's now go back to my original lecture. Well, it rotates once around in the period of your alternating current. If that is a 60 Hertz current, then it will rotate around with 60 Hertz, 60 times per second. And so if we put a magnet in here, then this magnet will want to go around, wants to follow this rotating magnetic field. And we call that a synchronous motor. So the rotor of such a synchronous motor itself would be a magnet, and it would rotate around with the frequency of your alternating current. But you need a 3-phase current for that, so that the magnetic field rotates. I can also place in here, this is again a horizontal surface. We have it here. I'm going to do it right here. Here are those crazy loops with the 3-phase current. We can also put in here conducting sphere, or in my case I will use a conducting egg. And when the magnetic field rotates around, there is a continuous magnetic flux change to the surface of that conducting sphere or egg, and so it's going to run eddy currents. Now if you have an eddy current going around and you have a magnetic field, then the magnetic field and the eddy current will cause a torque on the current. In a similar way, when we discussed earlier the idea of a motor that you were going to build, there was a magnetic field and there was a current, and that caused a torque. In the same way, you get a torque on the eddy current. And so it starts to torque up this conducting sphere. And all the time there will be eddy currents because the magnetic field keeps going around. And so you're going to get a torque which will always be in the same direction, and this conducting object will now start to rotate, and we call that an induction motor. Induction motors have no brushes. How fast the induction motor will go depends on the conducting object. If it is a sphere, it will probably come very close to 60 Hertz, because a sphere has many possibilities for eddy currents to run around. Whereas if you take a ring, and we will try that, if you try to spin a ring in a rotating magnetic field, then of course the various paths that are available for eddy currents are very limited. Can only go around in the ring. Many of the stationary tools that you find in people's workshops and in the basements are induction motors. A table saw and drill presses, also electric grass mowers, are induction motors. I want to demonstrate now to you what three-phase currents can do. And the first thing I'm going to do is show you that, that unit that we have here, which are the coils that I described, through which we are going to run the three-phase current. I must get my lights right. There you see it. Coils are wound in a very strange way. After class you can come a little closer. And so in here you would have a rotating magnetic field. We use 60 Hertz. It rotates around 60 times per second. And the first thing I'm going to do is something wild. A little bit in style, I suppose. I will put on top there a cardboard cover with little magnets. They're randomly oriented. There's no way that they can ever rotate. You know, these are these little magnets, flat, a lot of friction. If I expose them to a rotating magnetic field, then they will go nuts. I told you they were going nuts. You're not supposed to show this to students, but okay. Now here I have a conducting egg. And this now has ample possibilities for eddy currents to flow. And so now if I give these coils the right current, the three-phase current, it's spun up, the magnetic field acts on the eddy currents, and it starts to spin. And I have actually tried to measure the rotation rate. It's only a little bit under 3,600 RPM. 3,600 RPM would be 60 Hertz. It's very close to that. If I spin this object in the direction in which the magnetic field is not rotating, then it says, sorry, no way. It just reverses, because the magnetic field is going to slave it in the direction that it wants it to go. So you're looking there at an induction motor. I have here a ring. Now a ring doesn't have as many possibilities for eddy currents to run. Could only go around like this or like this, right? But I can still make it spin probably if I do the right thing. First of all, I have to rotate it in the right direction, which would be this one, I think. There it goes. It doesn't go anywhere nearly as fast as the egg because of the restrictive paths of the eddy currents. But it rotates. It's trying to follow that magnetic field to the best it can, but its abilities are very limited. And needless to say, if I try to spin it in the wrong direction, that of course it will stop, and it has no way, like the egg, to reverse its direction.